as we discussed before, as I wrote it. So my thesis is about Sagnac effect in rotating ring with Dirac fermions. My name is Andrii Fesh. My supervisor is Sergei Sharapov. And I will present results of my works and show what happened. So what is the Sagnac effect? It is a really long history of, it has a really long history of development back to beginning of 20th century when George Sagnac and his colleagues checked that there is some phase shift due to rotation of interferometer that has closed area. And this was the first evidence of, one of the first evidence of that support relativity. And after that, there was many confirmation of such experiment. And after rise of quantum mechanics, there was a proposal to test interference, Sagnac interference on matter waves like electrons, neutrons, atoms, and to this day there is many experiments that confirms interference pattern on electrons, neutrons, atoms, because of the nature of the matter waves and their scale and scale of the to light, having the same setup experiment, we can gain really big sensitive in this experiment. And this is what the our interest, that if we have Sagnac effect on matter waves in free space, how it will look like on the graphene, because there is really interesting property of graphene. It has high mobility, ballistic transport with some condition when we have millikelvin or 4 Kelvin temperature. It has Dirac quasi-particle liner dispersion, and it has really long coherence length, so we can make devices that can test some interference pattern on a really large scale compared to another ballistic coherence transport. And this is interesting to test how this relativistic properties will survive in crystal lattice under rotation. And right here you can see one of the achieved and created already graphene ring. Author of this article tested Aharonov bomb effect in graphene, and they confirmed that there is interference pattern because of external field gauge, yes, magnetic gauge. And this is really cool because then we can talk about testing not only Aharonov bomb effect, but also, for example, Sagnac effect, that also is like interference phase shift effect. And the problems is next. In the free particle, there is some really not clear description what we use for describing this phase shift. We can say that from relativistic perspective, we can say, and as in this formula, that we use full total energy of the particle and proper time dilation. And it is important to notice that when we expand this formula, we will get in the non-relativistic limit, non-relativistic in quotes, because there will be no time dilation in, of course, non-relativistic limit, but nonetheless, if we take out gamma terms, we will get that our phase shift will be proportional to the mass of the particle. And this is the question, will be for quasi-particles in graphene, interference will be also proportional to bare mass of electron, or it will be proportional to something else, to like effective mass, but there is no effective mass in Dirac fermions without gap. And what we want to do, it's like try to understand how it works. And I think there's only two correct ways to describe it. We can take like approach using non-relativistic quantum mechanics, because when we try to describe from the beginning this phase shift using only non-relativistic quantum mechanics, we also will get this phase shift because of the properties of quantum mechanics itself. It carries some trace, from the relativistic theory, or I don't know. I didn't see clear root where it's come from, its mass, yes. And I think maybe it doesn't matter. I think it matters that in the phase shift we describe waves that propagates through space, and they have n mass in the free particle. It's like parameter of the. It's like something that describe property of this wave, and for crystal lattice, we should use non-relativistic theory to derive this phase shift, or we can try to use or to suppose to create like a relativistic theory of quasi-particle that will be fully Lorentz invariant or something like that, or we can try to solve quasi-Lorentz invariant Dirac equation and see what it will be. And in a year ago, there was an article where I was a co-author about this effect, and we tried to derive this effect from the beginning using this equation for Dirac fermions, where we neglected spin effects, where we where you can see the dispersion relation, energy of the Dirac points, and if we will solve this equation using ansatz method, like this, for most of the cases, like it's okay. Then we will have this next results. Yes, phase, it's total phase, and phase difference will be like this. And as you see, it's depend on the dispersion relation of the quasi-particle. But there is a question, because is we fully know is algebraic structure of our relativistic quantum mechanics arrives in a crystal lattice. If you derive the formula, it gets us some results that we say that, yeah, it gives us phase shift. But it's not that clear, because in free space there is something like Bagman algebra that describe all of the transformation with the central extension as a mass. I will not dive deeper in this. That's because this doesn't matter. all this matter that mass is important in the relativistic quantum mechanics, and it's not clear what is it. And when we move to crystal lattice, I think that our dynamics of the system and this phase shift will be covered by the waves itself and the excitation. It should be, and it should not have any relativistic rest mass, because when we look at our derivation of relativistic phase shift, there is total energy, but when we expand it, there will be no mc squared. There will be also only mass, that like description of the wave. And if we try to solve this equation, solve this phase shift from the Schrödinger equation, we will get the mass from the kinetic term. There will be some caveats, because there is no time dilation, but shift will exist nonetheless. And as we see that mass is not going directly from the rest mass itself. It's like, it's a property of something like of algebra and waves in free space. And when we go to crystal lattice, I think that we should use our dispersion relation for quasi particles, not think about full energy of the particle itself, because there's like no particles.
Andrii, you almost finished your time.
Yeah.
Let's say
Okay.
3 minutes.
This is the end. And I will finish with this formula that we can reconcile this result from the article that you wrote that depend on what we want to have, like full energy and bare mass or dispersion relation. We can write like this formula where speed will be like parameter. And yeah, this I already said that. And the main question is in condensed matter, is this algebra preserves and how? And maybe it will be the key to have a solid base to prove that we will have only effective theory that will describe this phase shift. We do not need to talk about relativistic aspects. And that's all.
Okay, thank you. So could you just make this more concise, the conclusion? In fact, for example, I do not understand what is the difference between kinetic and effective mass. Okay, rest mass, I understand, but then what is the difference between kinetic and effective?
Okay, this is like I chose to say like that, because in many articles about Sagnac effect, there is like this statement: Sagnac effect is fully kinetic effect that's fully described by relativistic theory. Yes, and from this statement, we can think that phase shift should be governed by the kinetic of the system. But in quantum mechanics, kinetic and boost doesn't only governed by the in non-relativistic term, not only governed by the translation in space, but also by the mass itself. And this is really the difference between quantum and classical Sagnac effect, that we should think of mass like something that
No. I just wanted more shorter answer. I mean, effective. What is effective mass? It is something that includes both rest mass and kinetic mass, or what?
No. Effective mass is just mass that describe quasi-excitation of our curvature of our I don't know bands. Yeah, if we think from this perspective.
Okay, so it is indeed three different quantities.
Yes.
Okay. Okay, so thank you. Then let's it's open for the questions. Валентин?
Я маю, так би мовити, признатися, що я не дуже в цій тематиці розбираюся, але в мене виникло таке питання. Все ж таки, якесь відношення до цих ефектів має те, що ті загальні чи випереджальні хвилі по-різному інтерферують? Чи це зовсім з іншої опери?
Can you
Чув питання?
can you please repeat, because it was real.
Питання було, чи це має відношення до того, як там ці випереджальні, як ви кажете, загальні випереджальні хвилі інтерферують, яке відношення має до інтерференції. І, в принципі, я сюди ж хочу додати своє питання, тому що воно однакове. Мені не вистачало відповідно ілюстрації, пояснення. Скажімо, що ж таке Sagnac ефект і яка різниця між Sagnac ефект і Aaron-Bohm ефектом? От яка різниця? Це ілюстрації такої не вистачало. Ну,
Okay.
не мені, а загалом для.
Okay, it is really a tricky question because if we take like relativistic quantum theory, and we suppose that it is correct, yes, it is more correct than quantum theory, non-relativistic. Then we say that there is like time dilation of this excitation that moves through the interferometer. But if we look at non-relativistic perspective, there's no time dilation. There's something like effective gauge that we introduce into our equation, and maybe it's like also just a trace of this relativistic quantum mechanics. And this is true because I see some theoretical explanation of this, but it's dependent on what you want to hear. Yes, in most solid explaining is that yes, there is time dilation, and because of that we see this interference pattern.
What is the difference between Sagnac effect and Aaron-Bohm effect?
Aaron-Bohm effect is effect of interference that appears due to electromagnetic field that we introduce into our interferometer. So we put I forget the word. A moment.
Shift of wave function, right? Phase of the wave function.
Yeah, no. I forget how to say from electromagnetism. There is B, E, and A. I forget how to say.
Vector potential, you mean?
Yes. We'll introduce magnetic vector potential into this interferometer that will be perpendicular to our interferometer. And this effect is almost not classical, because we will not see it in classical mechanics if we take two wires connected and
Why it's not classical? It means that waves, it is classical in principle. If you speak about photons or light, it can be considered classically as waves. Therefore, it is in this
Yes.
sense it's classical. If you switch to particles, then considering its wave nature of particles, it's already quantum. Therefore, it depends which particle you are taking into account.
Okay, I will explain it in other terms. From at the beginning, how it experimentally looks. Imagine two slits experiments with electrons. You have two slits, electron we don't know where they move. And after the slit, we have a solenoid where we have inside our field. Yes, it's not.
No, it's already I think complicated, especially when we try to formulate it in English, which we all are not perfect in. And therefore it is additionally complicates the situation. But I would just simple difference. Could you say it's maximally simple? What is the difference between Aharon-Bohm effect and Sagnac effect? So Aharon-Bohm effect it is interference due to wave nature of the carrier. Wave nature of photons, or wave nature of wave nature of light, or wave nature of particle.
Not so quite.
Okay.
Aharon-Bohm effect is due to interaction between vector potential of the magnetic field, and
it is the reason of the phase shift. The reason of the phase shift is the field.
Yes.
But the origin of the effect is the interference due to phase shift. Right?
Yes.
What is Sagnac effect then?
It's like in a really fancy term, it's like geometrical phase shift due to relativistic time dilation interference of
relativistic time dilation. So this is relativistic effect.
Yes.
I see that Sergei Sharapov shows signs that he disagrees with it. Yeah?
Yeah,
Sergei.
yeah, yes.
Could you comment?
Okay. Should I comment just on Aharonov-Bohm or already like a discussion on general situation with this diploma?
No, probably only this short comment, and then we continue with questions, if any.
Okay, first of all, I advertise 2 weeks ago was a beautiful conference in Kharkiv, low temperature physics, and it was invited speaker Michael Berry. And he was talking about this, and it was beautiful talk. So if you have a chance, I believe that it was it should be in YouTube. So okay, why the Aharonov-Bohm effect? Andrei mentioned it. What is the reason? Aharonov-Bohm effect. This is the result of interference of quantum mechanical particle moving on two different paths, and the cause for the interference is the vector potential. The specific of Aharonov-Bohm effect that how it was designed, that the idea that there is difference between classical and quantum physics, that in classics we think that fields act on the particle. In quantum mechanics we start to talk about the vector potential. If you look configuration of the fields in Aharonov-Bohm effect, but Berry actually questions this, and this is currently under discussion, that in Aharonov-Bohm effect, on the passes where the electrons move, field is zero, and non-zero is the vector potential. So this is a tricky and clue feature about Aharonov-Bohm effect. Why? But common between Sagnac and Aharonov-Bohm effect, this is in both cases the interference of quantum mechanical particles moving in two different paths. Why we speak about Aharonov-Bohm effect in this case? That Sagnac effect in solid state is not experimentally realized as yet, although there are articles, talks, and so on. And the Aronoff-Bohm effect studies in solid-state systems, this is a mature area. And firstly, it was observed in semiconductors, I don't know, 20, 30 years ago. And now there is a vast literature about realization of Aronoff-Bohm effect, where people create these gated structures, apply fields, gates, and play in a very different way. So this shows that this area is quite mature to work on interference experiments. So this is the motivation. And finally, one thing which I should mention, but in this case, it will slightly create a mess with the mass, but all we know there is a Larmor theory in non-relativistic physics. So when some vector potential is actually equivalent to rotation of particle with certain mass. So in this case, there is even equivalence between rotation and vector potential. So those effects are actually, so if you know the answer for Aronoff-Bohm, you can expect the answer for Sagnac. And this is also present in the literature. Okay.
No, I think we all were missing the geometry of the experiment explained on your slides.
But Andrei should move. Andrei, please show the. You show the rings. You have everything. Oh.
No, not this ring.
Okay, so this
is
normally,
for Aronoff-Bohm effect.
Yes. For Sagnac, it does not exist. So this ring in the magnetic field, and we send the current from S1 to D1 and observe oscillations. Maybe it was better in the talk to show it. So these oscillations are related to the flux penetrating the ring. And you see how mature.
This is Aronoff-Bohm effect.
Yes, exactly.
Yes, it is clear. Sagnac effect.
Our theory expects that if you do the same configuration, if you, instead of applying magnetic field, rotate the ring, then you will also observe...
instead of magnetic field, you rotate.
Yes, exactly. But experiment for Sagnac is under proposals. It does not exist. For Aronoff-Bohm, tens of papers we saw.
Yeah, okay.
And you see pretty much large coherence lengths. You see the line scale in the 500 nanometers. You know coherence wavelength in normal metals. So it's actually pretty good characteristic, and it's actually very low temperature, millikelvins. All this maybe was better to write explicitly on the slide.
Okay, thank you, Sergey. Some questions? Можна українською, можна англійською. Можна німецькою. Немає? Okay, then I have a few questions maybe. Let's go to your formula, the main formula. Actually, what I'm lacking, it's just clear formula to see the effect, and it depends on what. Yes. So here is, let's say, the main question is about this omega zero, yes? How it is defined and what is the role of mu, for example. So delta, what is delta? It is the gap or what?
Yes, delta is the gap.
Delta is the gap, but there is no gap in this Dirac. Dirac.
There is no gap.
So it is zero for graphene. Delta should be zero for graphene, okay?
Yes.
And mu. So the question, what do you put in mu?
There is
And
dispute.
should be negative then? It is somehow strange a bit. Negative frequency.
There is because there it is phase when we will do measure phase. It will be like module of the phase, so we will not see this sign. Yes.
Okay, but let's say if we in some region where we close to where the kinetic energy, so it is the kinetic energy here. It's kinetic energy. This is kinetic energy. What is under the square root? It is the kinetic energy which is measured in respect to this crossing, in respect to the Dirac point.
Okay.
And then So, and if we are in graphene, it is 0, and then only what we have minus mu somehow. Okay, and what is the mu then?
Okay, mu is chemical potential. It's like energy of Dirac points.
Mhm.
Here is the flaw and the problems. First of all, kinetic terms, kinetic word for this dispersion relation is maybe not that applicable, and we should use just we have the dispersion relation, and it's explain us how energy and momentum and is related. Yes. So what does it say us? That we have linear dispersion, and we have some energy of Dirac points. And in the article, we said that because of really large mass, bare mass of the electrons in the general description of Sagnac effect in free space, we cannot omit this mass in the graphene. But I see there's a problem, and I cannot resolve it really clearly theoretically, but I see where the fits of this statement is going, and is when it's where it's
Okay,
from.
actually, I understand the answer. I understand the answer, but I mean, I understand that you feel it is not correct to put the rest mass, but you don't know how to do it and how to explain it. So I understand in such
Yes.
a way. Is it correct? Okay.